Self-driving cars have become increasingly popular nowadays, but self-driving taxis might be the ultimate goals of companies like Uber and Didi. To figure out a system that can optimize the overall reward seems essential to these companies in the future. So I choose to start from training one self-driving taxi to optimize its reward. In this third project, I will mainly use reinforcement learning technique to tackle this problem. Reinforcement learning is one of the main areas in machine learning. In a typical reinforcement learning problem, an agent will try to find the best policy to optimize its overall reward after training. Reinforcement learning doesn't require a huge amount of data as supervised learning or non-supervised learning does. It generates data during the process of training, and that serves as labels. And that's why it's in the middle ground of the other two machine learning methods. A reinforcement learning environment is formulated as a Markov decision process, MDP. It has to meet the Markov property. The probability of getting to the next state only depends on the current state. So it's a memoryless process. The environment consists of states, action that you can take at every state, and a reward for every action. A taxi environment obviously meets the Markov property. The probability of a taxi driving to Century Avenue at 12 p.m., for instance, doesn't depend on where it went to at 7 a.m. or 8 a.m. In the taxi environment that I created, we use simplified grid world city to represent the real scenario. The state is a tuple of time, row, column, passenger index, and destination index. Passenger index and destination index are represented by the location index. When there is no passenger in the taxi, both P index and D index will be none. If the taxi picks up a passenger at the shopping mall and he wants to go to residential area, then the P index will be 2, 3, and D index will be 0, 0. We assume that the taxi driver works from 7 a.m. to 7 p.m., which is 48 quarters. At each state, the taxi can take 7 actions: go up, down, left, right, pick up, drop off, and stay still. Moving from one grid to another has a reward of -1. Running into a wall or doing wrong pickup or drop off gives a reward of -10. A successful taxi trip has a reward of 5 times the absolute distance between the pickup location and the drop off location. To clarify a few more points, V1 setup meets the following rules. Requests are simulated based on real situation. For example, there will be a request from the financial center to the shopping mall at 12 p.m. because people want to go eat. And in V1, there is at most one request from a place to another at a certain time. And the taxi doesn't know when and where the request will be. Since the number of states isn't too big, I chose to approach the problem with Q-learning algorithm instead of using a function approximator such as neural networks. Q-learning itself is an online learning algorithm, which means it updates itself after every step the agent takes instead of waiting until the very end of the episode. And most importantly, in theory, it converges to the optimal policy. Q-learning is mainly looking for the best policy by iterating through the state action pair's expected value table. To avoid conversion to a local minimum, I used epsilon greedy policy. With the probability of 1 minus epsilon, the agent takes the argmax of the actions at next state to update the Q value of a specific state action pair. In other words, it's updating the Q table according to the Bellman equation. My hypotheses are as the following. The taxi will learn when and where to pick up passengers. The taxi will learn the shortest path from one location to another. And most importantly, the taxi will learn how to maximize the daily income. Tuning parameters is inevitable for every machine learning problem. I try to find the best combination of learning rates, discount factor, and epsilon. To evaluate how the combination performs, I follow these disciplines. Each combination will be trained for 10 times. Compute the average overall reward and its standard deviation. Observe the best overall reward and its standard deviation, and then pick the best and most stable combination. So when the learning rate equals 0.6, discount factor equals 0.9, and epsilon equals 0.3, the agent seems to have a pretty stable learning performance. A typical training process looks like the graph shown on the right. In reality, a taxi driver might get several requests at a certain time at a certain location, so I added more requests to the situation based on simulation. For example, there will be 2 requests at 7 a.m. at residential area, where one of them goes to a financial area and the other goes to the tech park. and respectively the action space has become a little bit bigger. Reward system still stays the same. A new hypothesis here is that the taxi will learn how to choose the best request that can lead to a trajectory that brings the optimal reward. When it comes to tuning the parameters, I use the same method as before. The only difference is that the agent is trained longer this time since the state action space has become bigger. Combination of learning rate equals 0.75, gamma equals 0.9, and epsilon equals 0.1 gives the most stable training performance. And a typical result of training is shown in the next video. However, after looking through the best overall reward, I found a surprising result. In most cases, the average overall reward the agent gets is 57, while after this training, the overall reward can get up to 92, which almost doubling 57, and that has become the new benchmark for training evaluation. The policy that returns a overall reward of 92 is traveling back and forth between the hotel and the airport. Apparently, the training most oftenly converges to local minimum, so this leads us to new questions. Why does premature convergence happen most of the time, and how can we improve the algorithm to avoid this issue? So I made the agent return the number of times that it has taken the specific state action pair along the very best policy. It turns out that the actions along the trajectory of the very best policy is rarely visited. Essentially, this is one drawback of Q-learning, that it looks for better policy based on the current best value found, and premature convergence can take place because it has bigger probability to be visited. It's hard to represent the multidimensional space, but it should be similar to this two-dimensional case. The local minimum 57 covers much more space. Even if the agent is discovering the 43 minimum, it will still tend to go back to the previous 57 minimum instead of more exploration. Therefore, premature convergence is more likely to happen. One possible way to avoid premature convergence is to decrease the learning rate with respect to the number of times that a state action pair has been visited. When training approaches to the end, set learning rate as a deterministic value. Back to the two-dimensional case, the learning rate will become small when n of SA has been visited a lot of times, hence it will take small steps. Otherwise, if a state action pair is rarely visited, and if it returns promising results, it will take a large step. Here, I chose a soft sine function to realize the idea of adjusting the learning rate with respect to n of SA. I was about to choose a reverse logistic function, however, the computation will become too large and it will cause overflow problem. I defined this new function as g of x and the new learning rate. Each episode will become the initial learning rate multiplied by g of n of SA. However, the improvement on the training isn't significant. It doesn't ensure a better result. For example, when learning rate equals 0.7 and gamma equals 0.95, the average performance is worse than using a constant learning rate. So g of x for now doesn't seem good enough to solve the problem of premature convergence. Another approach will be encouraging the agent to do more exploration. The real problem here is that convergence of Q-learning has to satisfy greedy in a limit with infinite exploration, GLE. To satisfy GLE, all state action pairs will be explored infinitely many times. Therefore, 150,000 episodes isn't enough to meet the requirement. I increased the epsilon and decreased the learning rate to train the agent for a much longer time. I set the epsilon as 0.1 in the last 5% of the training episodes and 0 for the last 10 episodes. A typical training result looks like this. New average score has been raised to around 70 points. However, there are still a few cases where the best overall reward still converges to 57 or even lower. So far, the project has brought up some issues of Q-learning. Q-learning algorithm ensures convergence, but not necessarily to the optimal policy. Longer training episodes is expected to return better convergence, but again, not necessarily. Combination of epsilon and learning rate is tricky to choose because it requires a lot of experiments. Due to the time limit, I only tested the performance of every combination 10 times. The goal here is to learn how to behave in the best way in the shortest amount of time. I will implement the GeoVax discussed earlier to larger training episodes, bigger epsilon, and smaller learning rate to see if it can reach the benchmark convergence faster. In addition, instead of taking a completely random action, I will see if there is a better way to sample the actions for the epsilon greedy learning algorithm. Thanks for watching.